Welcome back C++ learners. In our ongoing journey to learning C++, we have covered topics from basic syntax to numeric limits. Today we are going to take a look at type conversions. Understanding how type conversion work is fundamental to avoid bugs, unexpected behavior, and portability issues. So let's get started. When working with C++, objects can hold different types of data and perform various operations. One essential feature is the ability to convert objects from one type to another. These conversions happen automatically in certain situations, like when we assign values or use expressions involving different types. Let's explore some examples to better understand how this works. For example, if I define a variable of Boolean type, but instead of true or false, I assign a number to it, what do you think will happen? So if we assign 0 to a Boolean variable, the value will be converted to false. Otherwise, for any other number, the value of the Boolean variable will be true. We can check this by printing out the value of a. Okay, let's build and run. You can see that 1 is printed, which means the value of A is true. By default, when we are printing a value of a Boolean type variable, it would be 0 or 1. If we want to print true or false instead, we should use the std bool alpha like this. If I build and run, you can see that the value of A is true. And if I set this value to 0, build and run, you see that the value of A is false. Another example will be if I define an integer variable and instead of assigning a number to it, I assign a Boolean value to it. If I assign true, the value of b will be 1, and if I assign false, the value of b will be 0. We can test this by printing it out. And after building and running, we see that the value of b is 1. And if I assign false to it, it will be automatically converted to 0. If we assign a floating point value to an object of integral type, the value is truncated, meaning the part before the decimal point is stored. Let me show this in action. So I'm defining an integral variable named c, but instead of an integer value, I'm giving it a double number. Let's see what is stored in c. you can see that only the integral part is saved into this variable. If we assign an integral value to an object of floating point type, the fractional part is 0 and precision may be lost if the integer has more bits than the floating point object can accommodate. Let me define an integer variable and assign this number to it. Also, I will define a float and assign give it a name, float var, and assign the int var to this float. By printing these, we will find out what has happened to them. Duplicate this line. As you can see, the floating point value is 1, 2, 3, 4, 5, 7, 0, 0 and not 1, 2, 3, 4, 5, 6, 7, 8, 9. This is because the int type can represent a wide range of integers, while the float has a limited precision and can represent a much smaller range of values, around 7 digits. Another example will be assigning an out-of-range value to an object of unsigned type. This will result in the wraparound behavior, which we covered in our previous video, but we can test it again here. If I define an unsigned int and give it a value of -1, this will result in the wraparound behavior, and as you can see here, we will get the last number in the range of unsigned int. If we assign an out-of-range value to an object of signed type, this will result in an undefined behavior, which means that the program might work, it might crash, or produce garbage values. Programs containing undefined behavior may seem to run correctly under certain circumstances or on specific compilers. However, there is no guarantee they will behave the same way on the other systems or with different inputs. To ensure portability, it's essential to avoid relying on implementation-defined behavior, such as assuming fixed and known sizes of data types. Now let's focus on expressions involving unsigned types. Although we may not intentionally assign negative values to unsigned types, it can happen implicitly, causing unexpected behavior. We will explore how mixing signed and unsigned values in expressions can lead to surprising results. To do that, I'm going to define a signed integer. I'm going to give it a name I, and I will give the value of -45. And I will define an unsigned int with I will give a name u, and the value of 10, if I print the value of I plus I, we expect to get minus 19. And if I print the value of u plus I, where I'm mixing an unsigned integer with a signed integer, let's see what will happen. As we expected, the value of I plus I is minus 90. However, the value of u plus I is something unexpected. In this example, when adding two negative integer values, we get the expected result. However, when adding an unsigned value and a negative integer, the integer is converted to an unsigned value before addition. And this is because the compiler first sees the unsigned int, and therefore it converts the signed integer to an unsigned integer. And here again the wraparound behavior has happened. So when dealing with unsigned integer types, we should be very careful. If I define another unsigned integer called u2 and give it a value of 42, if I do the u2 minus u, this should be fine because u2 is greater than u. However, if I do the u minus u2, again something weird may happen because u2 is greater than u, and when we subtract this, the result will the compiler assumes that the result is an unsigned. However, it's a negative value, so an unexpected thing may happen. Yep, as you can see here. So subtracting a value from an unsigned type requires caution to ensure the result cannot be negative. An unsigned value cannot be less than 0, and subtracting a larger value from a smaller one can lead to unexpected behavior. And this brings us to the end of this session. Understanding type conversions and being mindful of unsigned types in expression is crucial for writing robust and portable C++ code. By avoiding undefined behavior and being aware of how conversions work, we can create programs that behave predictably and consistently across different platforms and compilers. Thank you very much for watching this video. I hope you have enjoyed the video. If you think this video was useful for you, please subscribe to my channel and like this video. Until next time, happy coding!